As I mentioned last week, today we will see another type of robot again. As last week we saw about drones, this week we will talk about robots with wheels. We will approach the problem in a similar way as we approach drones and articulate robots, robotic arms, meaning that we will start describing their kinematics, see what are the control inputs, what are the outputs, and how do we model it, direct kinematics model, inverse kinematics models, and so on. And if we have a bit of time, we'll talk a little bit about planning, which is a topic related to wheeled robots. So how do we plan the trajectory or the path of wheeled robots? Okay. So we'll talk about the types of wheels that we have in robots, and how by putting the wheels in different configurations we end up with different kinematic models for the robots. How do we move around? How do we describe the kinematics and modeling? And finally, if we have a bit of time, we'll talk about navigation and planning in space with obstacles and so on. Okay. So first of all, why do you think robots with wheels are useful? Do you have any? Okay, they can move around. And why is that useful? Such as, I don't know, can you think of an application of delivering something in a factory or not in a factory? On the street, it's becoming a trend now, delivery drones, not drones. We talked about delivery drones last week, but that's maybe in 5-10 years. What's already happening is like mobile robots that they deliver packages and so on. Or pizza. Yeah, very useful. Big market. Okay, any other applications maybe? Delivery is one. Cleaning, yeah. By equipping the robots, the wheeled robot with something else, what we saw already, a robotic arm for instance, or a brush or something else, we can, use the benefits of a robotic arm, but wherever we want, dispatch wherever we want. Yeah, so that's basically it. Mainly, it's flexibility of reaching locations that either it's too expensive for a human to go, or too tedious, or too dangerous. Another application, for instance, might be disarming bombs and stuff. There are robots that they go, wheeled robots that they go where there are bombs and they defuse them and so on. Or, as I said, a dangerous environment. Wheeled robots are used for what? Yeah, or for space exploration, right? We send all these rovers on other planets. Well, mainly Mars and the Moon. We haven't sent rovers, I think, anywhere else. A tractor, if it's driven by a robot and not by a human, maybe. To drive the robot, yeah. Big, yeah. Anyway, all these kind of applications. The idea is that all these type of robots, they have wheels, and that makes them mobile. What kind of wheels do we see? Very basic information. There are robots with fixed wheels, or at least some of the wheels are fixed, meaning that they cannot rotate. Okay? Or it's what we call centered wheels, where they rotate around the axis of rotation, the two axes of rotation of the wheels. So the one that pushes the robot forward and the one that rotates the wheel itself, they're intersecting, or they might not be intersecting. Okay, so this wheel rotates around this axis and around this axis. Okay, there are some more weird shaped wheels, like this Swedish wheel, it's called, or these omni wheels that are very used in robotics as well. Basically, the benefit of this one, do you know what it is? Can you understand from the design? Yeah, it allows movement in this direction, powered by the motor, okay? But it can also slide laterally. You don't control that, because the motor just rotates the wheel, but it has the possibility to also slide. In some applications it's useful, yes? Sorry, what? Yeah, exactly. Because they can slide and so on. Good. Now, when we put wheels on the robots, they're either bi-wheel, when they have 2 wheels, or tricycles, or 4 wheels, or omnidirectional, or etc. We will see the first 3 types today, and we see how we describe them, how we model them. Okay? The basic idea is that we want to control the robot, and what do we want to control in a robot? We want to follow a specific path, right? Say, go from here to there by following this line, or that line, or something, right? Usually the problem is about trajectory, following a robot, following a specific trajectory. Okay? So we start by discussing about a little bit and understanding what the trajectory, how can we describe the trajectory. The idea is that every motion, this is our proposal, let's say, every motion can be modeled as a rotation around the point. Okay? Of course, if it's a circular motion, the point is fixed. But if the motion is not circular, then the point is moving around which we're rotating. Okay? So, just to help you visualize this, let's say we have this path, this motion. This motion, we can model it as a constant rotation around the point, but that point is changing. Okay, so at every instance, I'm rotating around a point, and I call that point the instantaneous center of rotation, or ICR. Okay? Can you visualize where the point would be, let's say, when I'm at this part of the curve? The derivative would show me what? The tangent, okay, and the point would be, what relationship would it have with the tangent? Perpendicular to the tangent, okay. So I have this curve, my robot is at this stage at this moment. You say, okay, I take a derivative, I take like the direction of motion, so the velocity in a way, and I take a perpendicular to that, and that will show me the current point where the robot is rotating around. Okay? But where is it along this line? Yeah? So the more sharp the turn is, the closer it is to that, to my curve itself. Okay? The more shallow it is, or the less sharp, the center of rotation is further away. Okay? So you can see it's something like this, where I have sharp turns, the center of rotation is closer to the curve. Okay? Where I have not so sharp turns, the center of rotation, the instantaneous center of rotation, is further away. Why do I call it instantaneous? Because when the robot is at this stage, at this part of the curve, the center of rotation is up here. When it moves, the center of rotation also moves. So it will move from here to here while the robot is driving here. Okay? How do we calculate this length? How can we visualize it? And why does it have to do with how steep the curve is? Basically, it's like fitting a circle, exactly that point, and that would be the center of that circle. That's why the steeper the curve is, the circle will be smaller, the center of that circle is closer. Okay? If I have a smoother turn, okay, the center will be further away. Okay? Now what happens if I'm not turning at all? I'm doing like a straight motion. Where is the instantaneous center of rotation? I will call this ICR from now. Instantaneous center of rotation when I'm moving straight. Left or right? The correct answer is yes. It switches from left to right. The moment I go like left and I move straight, let's say it's on my left at infinity, but the moment I go to do a bit right, it suddenly appears at infinity on the right side. So it's weird to talk about this. But we see that basically this is related to tangentials and stuff. And you remember how the tangent function looks like? When I have zero angle, the tangent is 0. And then at pi over 2 at 90 degrees, it becomes infinite. And at pi over 2 plus 0, 0, 0 something, I have minus infinity. So it appears from here. That's how the tangent looks like, no? So from minus pi over 2, it's minus infinity. Until pi over 2, it's infinity. And then at pi over 2 plus something small, it goes back, jumps immediately to minus infinity. Remember this? So you can have a feeling why the instantaneous center of rotation also jumps from left to right infinity when I switch from straight motion to slightly right or slightly left motion. Okay? And you can see it here. For instance, at this part of the curve, my center of rotation is on the left side of the curve, and suddenly, whoop, it moves to the right. Because here I was turning left, 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 and at some point I started turning right, 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 right. There is, at some part of this curve, this very, very tiny part that I was just going straight, and that's where the switch happened. Okay? Can you visualize? Good. So this concept we will use a bit today, this instantaneous center of rotation, because I can drive the robot saying not go left by 1, 2 degrees, whatever. Say, okay, move now with the center of rotation at that distance, at that position. So I'm basically, what we will control is the length of this. So we go the other way around. The length of this defines how curved is my turn, basically. And by changing this length at every part of my trajectory, I change how much left or how much right I'm turning. Okay? So let's see, our first example of a robot is a robot with 2 wheels. Okay? And usually these robots with 2 wheels, they have 2 driving wheels, and sometimes there is a third one just for balance. Because if you have 2 wheels, the robot will go back and forth unless it does some fancy auto-balancing like segways or other robots they do these days. Which is very common, but for now we'll say, okay, we don't consider that case. Say that we have a third point or a wheel that is just for balance, so that the robot doesn't fall back or forward. Okay? And yeah, we have 2 wheels, and each one can rotate independently. Okay? How does that look? Let's have a look. So this is the top view of the robot. I didn't put a third stabilizing point, but the idea is that I have my robot, this is the box, and I have 1 wheel on the left and 1 wheel on the right. And this is how I see it from the top. Okay? This wheel rotates and this wheel rotates along this axis. Okay, and we will see how I can produce different trajectories by changing what? We'll see what is our input. Now, some definitions, I will use these terms a lot. There is this, we use the same letter for the angular velocity of the robot and of its wheel. Okay, so angular velocity of the robot means how fast is the robot rotating around its center. Okay, while angular velocity of the wheel is how fast the wheel is rotating around its center. Okay, the same for linear velocity of the robot and linear velocity of the wheel, u and ui. We need to know what is the radius of its wheel, or nominal radius of its wheel, so how big is the wheels, because that will affect my kinematics. And by big R, capital R, we will denominate the radius of the instantaneous center of rotation. So basically this distance from here until the center of the robot. You see here, at every part of the path. Okay? Now to describe the pose, the position and orientation of the robot, the pose. Okay, sorry, question before that. How many degrees of freedom do you think this has? No, sorry, what? Yes. Why? Can rotate and Okay, we'll talk about this and we'll see what is the answer. Or any more comments now? Any other answer than 2? 1? Which one? Only that? Okay, let's see. We will see. We'll come back to these questions. Okay. Now, how we describe the position and orientation of the robot? We have the, as I mentioned, we have the angular velocity and linear velocity of the robot, but this is on the frame of the robot. We need also a description on a global fixed frame. As we had for the drone and for the robotic arms, we had always a fixed frame that the end effector or the drone was referenced in that frame, right? So here it's a bit simpler. Why? First of all, because we talk only 2 dimensions. In this modeling, we will not talk about the 3rd dimension. Why? It's a drone. It's a mobile robot, not a drone. It doesn't change its Z direction. Okay, maybe the floor changes Z direction, but it's easier if we just model it as flat with some whatever. In general, we talk about a surface. Okay, so the robot moves along a surface, and we care about on the surface. We have 3 things, 3 coordinates. Of the pose, it's the x-y position of the center of the robot, and theta is the rotation along this on top of that plane. Okay, so this rotation of the robot. Okay, good. Now, what can we control about this robot? What we will consider a control input would be the linear velocity of the robot, okay, and the angular velocity of the robot. So that's what we call as u and omega. Okay. Is this what we actually control though on the robot? What are we actually controlling? The velocities of the wheels, right? You could say that we can also control the position of the wheels, but yeah, we will mainly talk about velocities today. Okay, so we can also say that our input is the left and the right wheel the left and right angular velocity, the left and right wheel angular velocity, or the angular velocity of the left and right wheel. Okay? So we'll see how we first model it like this, and then we'll see how we can use this, how we can express this as a function of this. Okay? Now, how do we, let's see, if I have this robot, I'll draw it here. I have one wheel, I have another wheel, and I said that basically I want this robot to follow a specific trajectory, and I consider that what's important for me in this case is what is the distance of the instantaneous center of rotation at that specific part of the trajectory. Okay, so this R. Now, what is the constraint of this robot in order to move along this trajectory with this center of rotation? What should happen in the variables that we're controlling? U and omega, or omega left and omega right, or another thing that we can consider as our input is the linear velocity at the left and the linear velocity at the right wheel. What is the condition so that this thing rotates around this point at this instance of time? The right wheels have to move faster than the left ones, right? Good, great. How much faster? How sharp the curve is, basically, we said that the sharpness we express by this distance. Okay? If this thing moves as a single object, and this one has to go faster than this one, why does this one has to go faster than this one? What can you understand from this schematic? Or maybe another question. Let's say I had another wheel here in the middle. This one should go faster than this one. What about this one? What should this one should do? Faster than this one, or faster than the right one? Or between? In between? Okay. So that's correct. It should be in between. So what do we see? The speed of the wheels has to do with the distance from the distance with this distance, basically. Okay. Good. Do you remember what did we say at some point? That if I have a circle that has a specific radius, okay, and I have an angular velocity in the circle, do you remember what was the resulting linear velocity? How were these strings combined? What was the linear velocity expressed as? Of omega and r. Okay? Good. Yeah, it's omega and r. Very good. So that would be the vector of the velocity. The magnitude, let's say we just care about the magnitude right now. So the norm of this vector would be the norm of this vector. It's basically, it's this without the vectors. It's the absolute value of, or would be basically this thing. Yeah, the absolute value of the magnitude of the angular velocity, magnitude of the distance would give me the magnitude of the velocity. Okay? Good. And here, in order for this object to rotate in a correct way, let's say not sliding, I would want that the instantaneous angular velocity of this point with this center would be the same as of this point with the center. Okay, so I want the angular velocity to be the same, right? So that it rotates beautifully. I don't know how to explain that. So, if I want this omega to be the same, what is the relationship between this u left and this u r with this omega? Yeah, which length? So this length and this length, right? So let's call this r left and r right. Okay. I know that this omega would be, according to this relationship, would be UL RL, right? But also it should be UR RR. Okay? The rate at which these 2 points rotate around this point should be the same. That's what angular velocity means. How fast are these rotating relative to this point? Okay? It's like having a cylinder but with 2 disks, let's say. If I want this to rotate as a cylinder without these 2 disks to slide relative to each other, then I know that the angular velocity is the same for this point and for this point, and I can figure out what would be the, I don't know, inner, external, whatever, velocity. Okay, so I know that this has to stand true, right? That's what I have here. The wheels must rotate in such a rate so that they rotate around the ICR with the same angular velocity. The angular velocity of this point relative to the ICR should be the same as this point relative to the ICR. Okay? Now, in order to make it a bit more beautiful, let's say, what we are modeling, as I said, is not this distance and this distance, it's the distance from the trajectory until the instantaneous center of rotation. Okay, so it's this distance that I'm modeling. So I need to express RL and RR as this distance R. Okay? And what would be RL relative to R if, let's say, this is length L? Too many things here. I have a drawing, you will see it clearer. So if I know that this distance is L and the trajectory is from the middle, I know that this segment is half of L, L over 2. So RL would be R, and then what is this? It's the big R minus this. So minus L over 2. And R would be R so R plus L over 2. Okay? And we know that these two have to be equal. Okay? So that is our constraint. If these two are not equal, then this object will not rotate around the center of rotation. One wheel will rotate around the center of rotation, and the other will rotate around another center of rotation, and the robot will slide, probably. Okay? Will not move along the trajectory. This is like a physical constraint. But the question is, the question is actually the inverse. I know that these two have to be equal, but then I want to know what value should I give to these two speeds in order to follow this trajectory, in order to respect this R at this instance of time. So how can I do that? I take this equation and I solve it for R. and I will get something like this. If I move this up, and I do the simplifications, I will get to this result. You can validate it if you want. It's just algebra. So now I have a model that tells me, if I know the curvature at this set at the moment, I know what value should I give to the left wheel velocity and the right wheel velocity. Or do I? Is this equation enough? If I say R should be 5 meters, whatever, and L is 2, can we solve this one? Does it have one solution? Why not? I have one equation and two variables. So I have many ways to solve this. Let's see some examples before we discuss about this actually. So we said that we control this radius by controlling the speed on the left and on the right. And at some point you said, if I want to go left, the right speed has to be bigger. Okay. So basically what we're controlling is the ratio between the two. If the left one is bigger, it will go right. If the right one is bigger, it will go. Sorry, if the right one is bigger, it will go left. If the left one is bigger, it will go right. Okay. What happens if they're both the same? We'll go straight, right? What did we say in that case we will have? Where will be the ICR? When I go straight? Infinity. What happens to the equation when I go straight? When UR and UL is equal, what do I get? I get a 0 here, so I go to infinity. Right? Left or right? Yes. What happens if one wheel is pushing forward and the other backward with the same amount? Rotate around the center of the robot. Hi. Where is R? In the center. So this distance is 0, right? So if UR is equal to minus UL, I get here a 0, right? When these two point opposite. And I don't get a 0 here because they will be either both negative or both positive. So it will be 0. It's not going to be any infinity. So you can see how this makes sense with what you already intuitively know. Now, we saw that this is not enough to determine the velocities. Exactly, it can show us the ratio between the left and right velocity, right? Why is that? If I have, let's say, a trajectory like this, and my robot is here, okay? And I know the instantaneous center of rotation. Is there more than two solutions for these two velocities? U, L, U right. We say that there is, okay? But how can what would be different, let's say, for different sets of good solutions for these two values, for this instantaneous center of rotation? What else can I change while keeping the same R? The linear velocity, right? So I can do this slow, right? Or I can do it fast. So I have more flexibility there. I have determined this, but without changing this, I can change something else of my robot, the linear velocity, or you can think of it the angular velocity, okay, without changing the R, okay? How is that? We need to remember the wait a bit. Yeah, we need to define omega or u as well. Well, u is the linear velocity and omega is the angular velocity around this point. Basically, what we can see is that the linear velocity will be equal to what? We say here ul and ur over 2. What is this? This is the media, the mean of the two velocities, right? If these two velocities are the same, say 1 and 1, it will be the velocity of the two wheels, right? The media will be the same as the one. If they differ a bit, then the linear velocity will be part of it, media of it, the mean of it, right? Now here I also wrote it in the form of I have here the linear velocity of the wheels, and I also transform it as the angular velocity of the wheels, because that's actually what we're controlling. I write this again and again. We saw that the angular velocity and the linear velocity are related. U equals omega r, right? So if here I replace for the angular velocity of the right wheel, it will be ur times r and ul times r being the diameter of the sorry, not the diameter, the radius of the wheel itself. Okay? So basically, knowing, yeah, now, sorry, one step back. So we saw here that by defining the instantaneous center of rotation, we don't define fully the velocities, but if we have also another equation for the velocities, and I know I want to have a specific linear velocity for the robot, then I have two equations, I have two unknowns, so I can solve this exactly, right? Or I can do it with the angular velocity. If I know that this is my u, the linear velocity, and this is how I express the center of rotation, and I know that this formula is correct, I can calculate also for omega what is the relationship of the two linear velocities of the wheels or the angular velocities of the wheels. Okay? I'm not doing the math here. Basically, I put this equation with these two factors here, these two actually, and I get this result. It's nothing extraordinary. I put the r on the left side, these two terms go away, and this is what remains, and the 2's go away as well, and L is down. Okay? Now, let's see again what happens when the two wheels are moving in the same direction with the same magnitude. What happens to the linear velocity? We said we get the media of the two. If they're equal, it's the value of the velocity. Okay? This one goes to infinity. You saw, right? Because these two are equal. And do I have any angular velocity on the robot? No, because ur is equal to ul, so this becomes 0. Right? What happens when they have negative opposite values? We saw that the linear velocity will become 0, so it will just spin. The center of rotation will be 0. Okay? And the angular velocity will be this minus this, but this is minus, so it will be 2 times the linear velocity over the length. You see? Which is what we expect. The thing will just have angular velocity, will have no linear velocity, and the center of rotation will be in the center of the robot. Okay? Now, let's try to transform these equations into a model and express the linear velocity and the angular velocity of the robot as a function of the linear velocity and the the angular velocity of the wheels. So linear velocity of the robot, angular velocity of the robot as a function of angular velocity of the wheels, because that's what we actually control. I can write this a bit more elegantly. Let me erase this. So I have u equals omega r plus omega left, the radius of the wheel, over 2, right, and omega equals to r minus omega l over l, right? Yeah. So I can write this in a slightly more elegant form like this. Okay. See, this is just in a vector format, where I have my u and omega, and I have my control inputs, omega r, omega l. And this I can write basically as r over 2 omega r plus r over 2 omega l, right? And this one is r over l, omega r minus r over l omega left, right? I just take this out and I have my, so I do this minus equals to this. Okay, just for simplicity. Now, this one gives me the linear and angular velocity of the robot as a function of the angular velocities of the wheels, right? Is this what we need? Can I control the robot using this? We need the inverse thing, exactly. For a desired velocity, angular and linear, what should be my wheel rotations? How can I do that? It's easy, what? Take the inverse of this, put it on the left, and we do it. Or we can do it from the system of equations basically I will end up with something like this, where I have the now, yeah, detail. Here I can have the angular velocities of the wheels as a function of the angular velocity of the robot and the instantaneous center of rotation, or the linear velocity of the robot and the instantaneous center of rotation, right? Because we know the relationship between omega and u, it's fixed. It's this omega times r, big R, equals to u. Okay? But now I want to come back to what we were discussing a bit earlier about the degrees of freedom. How many degrees of freedom do we have? Basically, we see that we keep on playing with these three things of the robot. And we saw that by defining just this, I still have flexibility to play with this, right? Or with this. But I cannot change all three of them at the same time. Why not? Because these three things are related to this equation. Okay, so the moment I fix the two, the third one is also fixed. Right? If I have just this one, then I can choose these two. But if I choose linear or angular velocity, then I have defined the other. Okay? Equally, I would say I want to play with the velocity and the linear and the angular velocity, and then my instantaneous center of rotation would be specified automatically. So I can choose any of the two of them, and the third one will be defined. Yes? Yeah, the capital R is the instantaneous center of rotation, or the distance, yeah, the distance from the center of the robot until the center of rotation. Okay, while the small r is the diameter, the radius of the wheels. So these wheels here, this distance, let's say. Okay, it comes up in the equations. Why? Because this radius will affect this linear velocity that I get here at the wheel. The bigger the radius, the bigger the velocity will be for the same angular velocity of the wheel. So here I have both small r and big R. But this R and this L are design constraints of the robot. The robot has a specific diameter of the wheel and radius, and it has a specific length. What I choose by choosing the trajectory is this big R, and then I can choose the U and the omega. The U or the omega. Okay? Now all these are expressed in the frame of the robot. So we're talking about linear velocity in the frame of the robot, angular velocity in the frame of the robot, and so on and so forth. If I want to do something on the floor, I need to express things in the frame of a static frame, a world frame, let's say. How could I do that? Which of the things on the screen do we know how to calculate? And which of the things on the screen we don't know how to calculate? Sorry? Theta, xy, okay. And what do we know? Do we know what? Or let's say u. Okay? Because UL and UR we kind of control. Let's say u. Okay? And we also know how fast the robot is rotating. It does not appear on the screen, but we know how fast this thing is rotating. Okay? Basically, we describe not the positions, because what we're controlling is not the position of the wheels, it's the velocity of the wheel. So the kinematics and the world frame, we also talk about velocities. Okay? And let's see if we can come up with a relationship between x dot. So the velocity in the x direction. What do you think it would be? The velocity in the x direction, according to what we know. The linear velocity in the x direction. Very good. So I have this vector, u, and I just need to take the component in the x direction. And that would be u times cosine theta. Y would be u times sinus theta, and theta. So how fast is this angle changing? It's what? The angular velocity. It's exactly the same thing. Right? Good. Can I write this in vector format? So this would be my vector. This would be another vector. What should I multiply here in order to get this relationship? First of all, what should be the dimensions of this? 3 times 2. Great. What should I have here? So I get x dot equals to u cosine theta. So I should have cosine of theta. Here, 0 because I don't have. So here I have 0 times omega. Okay, here, sine of theta, 0. Here, 0 and 1. Very simple. How do we calculate? So now we found a way how to calculate the linear and angular velocity in our world frame as a function of the linear velocity, the linear and angular velocity on the robot frame. Okay? How can I do this with the things that I'm actually controlling? So the angular velocity of the left wheel and the angular velocity of the right wheel. What did we see earlier? Do we know how to express this? Yes. Where was it? It was here. So if I multiply this matrix with this matrix on the left, so basically this thing is the thing on the board, this thing. So if I replace here this times that matrix times this thing, it will be our solution. Let's not write it. Let's write cos theta sinus theta 0, 1, 0, 0 times r over 2, r over 2, r over L minus r over L. Okay, this is a 3 by 2, this is a 2 by 2, this is a 2 by 1. So I can do the multiplications, right? And I end up with a model that I know how to control the output velocities as a function of the wheel velocities. Okay? How do I do the inverse? Because I want to know what should be my angular velocity and linear angular velocities for a specific desired velocity. Can I just take the inverse matrix? Why not? Why not? You are a bit sleepy today, I think. Why can I not take the inverse of? Basically, this will give me a resulting matrix which shows me the relation between this and this. Why can't I take the inverse? What's the dimension of this? Can I take the inverse of a 3 by 2? Second, third year, 2 by 3. You will take in algebra. You cannot take the inverse of a non-square matrix. Huh? We could take the pseudo-inverse as we did for a Jacobian in robot arms, or we could just work out the equations. I think that's going to be easier because the equations are not so difficult. As you see, there are no sinus cosines appearing. Well, they do actually here. Yeah. bad point. But anyway, we can work out the equations because they're not so complicated as they would be for a Jacobian of 6 by 6. Okay? Shall we take a small break?